So this is the first session right after lunch, and it's a kind of a DP mathy tutorial. So you might, just a perfect recipe to doze you off for the time being. But I'll try to keep you awake, and it's got a lot of content. The way I'm going to go through that is first present you with the business case. What are the challenges? What are the problems? And then I'll delve into a bit of a solution. Since it's only 30 minutes that I have, it's going to be hard to explain the entire solution stack. But feel free to reach out to me through various different contexts, or I'll be out here, answering most of these questions. Okay. So first things first. Let me see. Okay. Marketing campaigns, we have all been subjected to at various points in time, right? So so if you get an email, you get a phone call, you get a direct mailer, and most of the time it kind of works out well, but sometimes it just goes horribly bad. And if you are getting too many of these campaigns, then there's some person like me who are behind this trying to chase you out to buy for the service. So in that context, I've just kind of framed up a problem here. So we have marketing leads that are exposed to numerous channels. That's a factor of our life today. People are chasing you to sign up for various different things. It creates a very intercomplex channel relationships, right? So one of the challenges that we as a marketers actually face is that how should I value a channel? How should I attribute towards whether should I invest into a particular channel, A versus B versus C, and how do I stack its progress kind of going forward? That's a very difficult exercise because channel interactions have been out there and studied for about almost 2 decades, but there is no clear answer to this whole story. So this is going to be, I'm going to chase this problem once again, and try to find out an answer that what can be, more realistic when the new technologies, new models, and especially deep learning models are putting up, a lot of promises. Can I go ahead and solve this problem through that technique? That's the crux of the entire presentation here. So imagine there are 3 folks, right? A, B, and C. All 3 of them are getting different channel treatments. Okay, none of the 2 are going to be alike. That's a hard fact. Now, how should I choose my sequence of channels from A to B to C? Is there a technique, or can I just go random? But before we get into that, there are certain facts that you wanted to know. Channel touches can go from 1 to almost 100 or 500 of them, depending on how far go back you go and look and see them. If it's 3 months or 6 months, they can range from 1 to several hundreds of them. If you're doing a little mathematical calculations, if there are 7 channels, there are 15 touches. It's very nominal. 15 touches is not too large. Do you know that your possible ordered sequence space is about 5 trillion? Humongously huge number. Okay. How much of evidence do we have? Okay. I would be happy if I get a 5 trillion observations and model the entire thing up, right? But you're never going to get it. Okay. I would be happy if I get even a 1 million observation in a span of about 3 to 4 to 6 months. Okay. This is all you have to model it. Okay. So how do I model that little? So 1 million is just a fraction of $5 trillion, that huge space. How do I go about modeling that Sparse E evidence that I have today to find a solution in what's the best possible sequence to touch? So, like everybody else, if you get an AI hammer, you strike it. If you have known, if anybody has studied deep learning, and I think that's promising field, there's a technique called RNN, recurrent neural nets. We actually delve directly into sequence problems. So what I did first was pick out the RNN architecture and use it against the deep learning technique. So here's what I find. Okay. I apply a deep learning architecture. On the vertical axis, you see the odds of conversion. Okay. On the horizontal axis, you're going to see that how much a channel is making an impression towards an odds of conversion. Simple, right? Not too complicated. Right side, you see the architecture of the RNN, very decently given architecture. And when I model this through an RNN, this is what I get. I get a 0.4 odds when you apply an ad, followed by email. The odds go up to about 0.85, nearly about 0.9. Given a phone impression, it falls back to about less than 0.2. And then again, wobbles to somewhere about 0.8. Right. Now, yesterday there was a talk about business intuitions. Let me bring in that topic, right? You take this, go to your marketing manager, tell him that, all right, give ad an email to your potential lead, and your odds of conversion are going to be 90%. But do not subject him for any other phone call or anything else, or else the odds are going to fall down to 20%, right? I go back to my marketing manager, give him that story. He looks at and stares at me for a minute, deep stare, trying to give you, what are you talking about? One impression is wobbling your entire odds from 20% to an 80% to 90%? Are you crazy? Why should I believe you? Business intuition. He's been out there 2 decades trying to do this theory, and he has never found that golden sequence that he's out looking for. Okay. So I'm scratching my head. Is that the right way to do even to solve a problem? So sometimes you have to, deep learning or AI hammers, they're not just like, strike and, put the stuff, get the results out, and throw it away. Okay. That's not the way it actually works. There are hidden problems that you need to be very, very careful and very, very be aware of. Otherwise, you're going to fall into these kind of traps very often, very quickly, and you're going to make a miserable life of your own, and not only yours, but the entire organizations very quickly. So we just walked through that, 40%, 93, 20, and 80. So we see that there's an increase of 2 folds, and then drops to again to 20% in just a matter of 4 steps. Okay. I hope you get the gist of the problem that we're trying to chase here. Okay. There's certainly something else is going on behind the scene that we are not able to capture. Okay. Look at the points out there and measure them with the graph below, right? You see the points of discontinuities, which are the extremities that you actually observe. If you go back and check that why is this happening, you'll see the ratio, which is a golden to a blue bar, is extremely skewed in certain cases. Very, very skewed. Golden is, you can term it as yes versus no cases, positive versus negative cases. It's extremely skewed in these 2 situations. And that was not very apparent when you first time you go ahead and model this thing. What has happened is that the RNN has actually memorized these 2 discontinuities and just presented them as if it was the golden sequence. Okay? If you're not very careful about it, you're going to fall into these traps very often. Okay? So let's take a different approach. So from my observations, and I've been dealing with this problem for several months now, okay, what I figured, and this could be the reason, is happening because it's not about data is incorrect. The data is incomplete. Remember the notion that we just talked about? I have 1 million evidences, 5 trillion possible spaces. Okay, if you have this kind of situation, your data universe is incomplete, and this is why it's giving rise to such a problem. All along this while, I've been modeling the symptoms. I've not been modeling the true features. The true features of a problem is unobservable. You cannot observe them. But that does not mean you go ahead and start modeling the symptoms. If you can start modeling the symptoms, you're going to again start facing the same problem. Longer the sequence, the worse it gets, and higher the number of channels, the worse it's going to get. Okay, that's a given fact of this. Can I improve over time with more data? Yes, you can. But it's going to take a very, very long time for you to capture the entire space. or possibly not even close to it, right? What are my confidence in this result? At least from this technique, okay, you can go about saying that, okay, let me present this technique, but can I give a degree of uncertainty into it? The way you model from RNNs, you possibly cannot do that. That's why you have to revert to a Bayesian approaches to solve these kind of problems. Can I get most promising sequence? And what are my next best actions? Okay, we're going to chase these questions right down into our next slide. But before we get into, if I haven't lost you, this slide will certainly going to lose you in a moment. So let me not get down to the crutches of a technique, but it's all out there in my references. But if you apply, the technique has been adapted from variational encoders, okay, which is nothing but a deep learning technique today that we are using it to regularize many of our models. Not only a sequence-based model, but also classification, but also regressions. A lot of regularization has to be done on a deep learning technique before you can actually go ahead and apply them. First thing when you look at deep learning model is basically look at the loss, okay? The first question you should always ask is, what's my loss function, right? The loss function right now is given to you in a red box. Let me try and break it down for you here. It's composed of 3 terms, okay? The first 2 terms are multiplied by a factor called beta. Okay, not to worry about it. I'll get back to that in a moment. The last term is basically a reconstructional error, which is nothing but a classification. It's nothing but a classification objective function. That's all. Okay? The first 2 terms is actually a regularizer with a multiplication of a term called beta. Beta is actually a knob, which you can move. It's up to you as a human being. When you apply this, how far do you want this? How far you want to sacrifice on your accuracy and compress the data space? Okay. I will show you the visualization of data space, and in that context, you'll be able to see that what it is doing to a problem. Okay. The rest is all clear. Once you have the, a loss function, creating a marginal probability of a new data point is nothing but solving this equation, and a variance of that particular point is actually going to give you uncertainty. So this is all cool. It follows very quickly. But let's kind of keep focusing on the latent space. So what this technique actually does, okay, let me come back to you on this particular slide in a moment, but this is a Bayesian inference queries that we actually use on top of an RNN classifier to actually drop graphs and do a conditional query on it. Okay. I put up this slide to make sure that it's actually complete because we are using a Bayesian approach in trying to solve this problem. So what in a conditional query system, what we actually do is that if I have to find what are my odds of conversion of a client, which is actually your last node on the graph, if you look at it, given that web is equal to 0, so what I do is actually I do not take web nodal point into consideration. And if you look at the golden arrow paths, this is what's going to give me a conditional sequence, and I have actually eliminated the web portion from the querying system. Okay. Okay, it's not necessary. Let's go back to the architecture of the entire stack. Okay. So this is the architecture of the entire stack that is being currently used today. The left-hand side is nothing but your regular RNNs, which I feed in as a sequence to give me an output. But in this case, it does not give me an output of a point. Instead, it gives me an output parameter of a distribution, which I'm mapping it to a latent space, and I'm using the features of the latent space to give you a classifier towards the end of it. So why is this? Why do I have to revert to these kind of techniques to do that? Remember, if I compress Remember, I have very sparse evidence to actually begin with, right? There are lots of points, and there's lots of vacuum between that observation that I have no signal for, okay? So what I have to do is basically, in the name of regularization, I'm compressing that space into a measurable area. That's all I'm doing. Think it of in terms of, if you're a physicist, if you do not know how to actually measure a particle, right, you convert it into a waveform and measure the waveform. This is exactly the same analogy that's being done here. Every point is now actually converted into a distributed space, into a latent space, okay, not into its original space. Okay, the good part is that you can actually visualize that latent space. You can do an arithmetic on that latent space. You can do any kind of other algebraic operation in that latent space. It's all valid. Now, that is a beauty. That's a beauty that we never had up until now when we started to put it up. So when I saw that we're going to visualize the latent space, this is how it actually looks like, isn't it? It's all the points are now getting merged, and they're getting into a wavy form. It's actually getting into a distribution form. It's no longer a point. It's no longer a particle. It's actually an energy band. It's actually a waveform. Okay. The other point they actually note in this entire graph is forming a cluster. So red points are all, colluded together. They're all cobbled together, and the green points are all cobbled together. Red is the point where I don't want my sequences to end up. Green are the areas where I want my sequences to actually represent it into a latent space. Okay, red is a no-go, green is a go, right? So good part is that you can actually visualize it. The other good part about this space is that it is bounded, right? Against my original observations, which were 5 trillion, I could not even imagine how and where this would actually spot up. In this case, it is compressed form. It is actually bounded between V1s and V2s. What I do not know is what is V1 and V2, but that is okay. But I can still do an arithmetic on this particular space. That is more important. So, so if I get this wavy form, and I can do a linear, I can do any kind of a latent space algebra on this, I can always find what is going to be my golden sequence. You see, any of the optimizers that you apply, right? Any of the optimizers that you apply today, they require a bounded space. There's nothing called a global optimizer even today. But if given a bounded space, most of the optimizers will do a very good job. Okay? So this is the beauty that I'm trying to harvest here. As long as I get a bounded space, I can apply a lot of optimizers to find a solution to it. So, all right. So let's see how it all turns up. So now this time now, you remember the wavy discontinuities from the earlier slide. This time now I put an RNN through a regularizer, okay, and see how the points turn up. What happened was, the golden is a new point, and the blue was your original point that we actually saw in our previous slide. Okay, put in an ad, go with an email. The blue point actually jumps up, as we have seen that earlier. The golden one does not jump up as much. Okay, much more sanitized result. Marketing manager is not going to yell at me saying that, how come just with one impression you have taken from point 2 to point 8. So it's not happening anymore because it has forgotten that memory issue, those edge cases, those boundary conditions are all gone now. Okay. Same situation when it actually comes down. You put in an impression of a phone call. The regular RNN is going to dip down to a level unseen below because it was memorizing that sequence. Now it is not memorizing it. Okay, see the golden. It is just dipping slightly below, but it's not telling you that this is it's not following the blue pattern at all. And same goes with another touch point. Okay. So point here is that even if you have these discontinuities that you're actually seeing it, when you do a regularization, the jumps of the patterns do not happen. Okay. Now, maintains a consistent range over probability, and this is exactly what you're after onto. But that's not the whole story, right? Now comes the fun part. Now comes the beauty of the entire approach. Look at the uncertainty estimates, right? And this is what you're after, right? If you give one impression, who can be sure of in this world that is going to convert into a lead is going to convert into a client? But as you start giving more and more impressions, right, it starts to narrow down. And it is going down to a point where we can speak of with a certainty that this sequence, whether it's going to likely to happen or it's not likely to happen. The conversion is likely to happen or not. Okay. We never had this approach when we went around first time modeling through an RNN. Okay. This comes up only if you apply a Bayesian approach on top of RNN to derive you these results. Okay. So now I can go back to my marketing manager saying that I'm certain, after seeing the 4 sequences, I can say that odds of conversion are going to be at somewhere around 0.4, but I'm very certain that this is what the solution is going to look like, rather than giving him a 0.9 odds of conversion with a wide variance, which nobody has any clue what to do with it. Looking back at the space vectors once again, here's the other fun part. Let's say my sequence lands up into a point A on my latent space. Point A is in red zone, right? I want to move away from red zone. I don't want to be in red zone because reds are non-converts. These are no-goes for me. Can I move to a point B, which is in the center of a dense green zone, right? Remember I told you that we can apply latent algebra on that, latent space algebra on this thing. All I have to do is check with each possible combination, where do my vectors go? If I apply a phone to a point A, a web offer to a point A, ads to a point A, this is how my vectors are going to span out in that latent space, right? And if I have to go from A to B, another one, email is going to go in this direction. And if I have to go from A to B, apply phone, email, and phone again. Magic. It's not really magic, but it is something to go after for, right? Instead of applying things at random, right? All these field experiments are very expensive, right? They don't come cheap. Let me give you that. Giving a harvested solution is possibly worth it to everybody's everybody's time, energy, and cost. Okay. Give this to a marketer and say that instead of going random, apply this sequence. Okay, you will have possibly a better result. And then go in for the field trials, and then come back. Whatever the results are, if you refeed into the whole situation, you will be making a much better and an informed decision rather than working something which is totally out of the way. So I hope you're getting the gist of this. The mechanics is pretty involved, but I don't want to get into that since I only have about 5 minutes to go. But here are, we did talk about next best action, and we did talk about the optimal sequences. Everything is coming out of the latent space algebra, nothing more. Your work has now been reduced to just algebraic equations, and that is it. Okay. Takeaways, right? Small data sets, RNNs are going to memorize them very quickly. Deep learning is an approach, but you have to handle it very carefully. It's a double-edged sword, right? This is what I have figured in the last few months, hundreds of hours of work on it. It gets worse when the possible space is large. We did see that. If I have a possible space of 5 trillion, or more, and if I have evidence of only a million or so, this is going to get worse. So do not go ahead and start applying your model to symptoms. Avoid modeling symptoms, model on the true latent features, right? Weigh in the sequence by strength of evidencing. That comes from the Bayesian network. So instead of last end of being a classifier, you can actually take you can take any classifier, but I've taken a Bayesian classifier because it gives me the uncertainty of the results towards the end of it. So I can pick the latent space feature vectors, put into a Bayesian network, and work from it from that point onwards. Okay. We did talk about model in latent space. Do not model symptoms, and regularize through prior distributions. In this whole context, I've taken the distribution to be a Gaussian. There is no need to go Gaussian. Gaussian is I'm only taking because it's mathematically feasible. You can take a wheel-bull distribution. You can take a Poisson distribution. As long as it's differentiable and deep learning can adapt to it. Deep learning, all it requires is any kind of functional form which is continuous in space and is differentiable. As long as you can pick any of the functional forms, you can go ahead and apply to it. Okay. We didn't talk much about disentangled variational encoders. Remember, this was the factor of beta, which I actually conveniently left out just to avoid confusion. Now, beta is a parameter that you actually choose. And it's not something that is propelled from your data. What it does, essentially, is that it can elongate your latent space, or it can compress your latent space. That's all it does. If you elongate your latent space, the waveforms that I just talked about start behaving more like particle forms. If I compress them, the particles start behaving like waveforms. Okay, so if I have to go for waveform, why don't I just compress it? But there's one downside of it. Okay, more you compress, the lesser is going to be your accuracy of a classifier towards the end of it. That is the problem. So it's up to you how much of accuracy you want to sacrifice, and how much of a latent space features you want to extract. Now that's the tuning part that you have to actually choose as a scientist, as a decision maker into your problem context. Make sense? And then, as a bonus, the latent space actually opens up avenues for any kind of vector arithmetic. It's all applied and valid here, just as embeddings are. This is just another form of an embedding. That is nothing more than that. What is difficult right now is to find out what these vertical and horizontal latent space actually signify. They cannot, it's very hard to actually project them to a real-time meaning. Okay, and there's a very area of active research right now that how should I untangle my vertical and horizontal axes in a latent space. Okay, and what do they represent? In a geometrical form, they can represent how much is the inclination of an object is, what is the coloration, what is the texture. But when it coming to a sequences like a channel impressions, right? They don't really mean much. What does an inclination mean? This is an area of active research that has to be dealt separately. That what do these actually represent? If you can once and find it out, it'll be really cool. I'm almost out of time. Here are my references. These are the references that I would encourage if somebody is interested in pursuing this further. This is the area, all of them are basically an area of active research. These are papers coming out from last 1 to 2 years into this space. And I would certainly encourage you to read the last reference, which is called elbow surgery. I find it very fascinating, the way they have dealt with mathematics here. So it's a little of mathy, but if you're conversant with and not afraid of probabilities and rules and integral calculus, I think you should find that very handy to go. All right, with this, I actually wrap up my conversation. Thank you, folks. Let's stay curious until robots take over. All right. That's all for now. I hope you enjoyed it and learned something new today.